A lay-bound Japanese convoy, 8 transports under 8 destroyers, entered the Huon Gulf on March 3, 1943. 5th Air Force and RAAF strike groups attacked in waves. Post-action collations recorded all 8 transports and 4 destroyers sunk. Of roughly 6,900 troops embarked, only a fraction reached Leh. Tally sheets distinguished delivery methods. Low-level mast height and skip bombing produced hit rates in the mid-30% range. Medium-altitude level bombing remained in single digits. Only months earlier in the same theater, late 1942 claims averaged near 3% against maneuvering ships. The measured shift matched 2 linked adaptations ordered by Lieutenant-General George-C-Kenney and engineered in theater by Pappy Gunn. Low-altitude skip and mast-height attacks. B-25s converted into heavy forward-firing strafers to suppress shipboard guns in the seconds before release. The convoy's destruction turned spreadsheets into evidence. How, inside one campaign season, did field modifications and new attack geometry convert a medium bomber into a reliable ship killer? An after-action bundle sat on Kenney's desk in Port Moresby. Sortie counts filled the first page. Aim point photos showed bomb splashes in empty water. Missed distances measured in ship lengths, sometimes hundreds of yards. A margin note in red pencil underlined the number, 3%. That was the hit rate against maneuvering ships. 3 bombs out of every 100 released found their target. Pre-war doctrine expected level bombing to disrupt convoys and sink warships. Medium bombers would approach at 10,000 to 12,000 feet, above the effective range of light anti-aircraft guns. Bombardiers would track speed and bearing through the Norden bomb site. Bombs would bracket targets in a pattern. Statistical theory suggested that even if individual bombs missed, the volume would overwhelm defenses. In practice, maneuvering ships at sea reduced accuracy to negligible levels. A destroyer could alter course 20 degrees during the 30-second bomb fall. The aim point became historical data the moment the bomb released. Lieutenant-General George-C-Kenney arrived in Brisbane in late July 1942 to command the 5th Air Force. He inherited a demoralized command struggling against Japanese expansion in New Guinea. Brigadier General Ennis Whitehead served as his deputy for operations. Squadron leads from B-25 Mitchell and A-20 Havoc units reported the same dismal pattern in debriefings. Bombs fell. Water erupted in geysers. Ships steamed away undamaged. Japanese supply lines to Leh and Salamaua remained viable despite repeated raids consuming fuel, ordnance, and crew rest. Standard loads consisted of 500-pound and 1,000-pound general-purpose bombs fitted with instantaneous or short-delay fuses. Aircraft carried limited air-to-surface radar, primitive by later standards. Enemy screens mounted 25mm Type 96 and 13.2mm anti-aircraft guns in multiple mounts. The technology existed on both sides. Bombs worked. Fuses functioned. Bomb sites calculated trajectories accurately, but the geometry failed. Ships moved. Bombs fell through empty space. A 5th Air Force operations summary compiled in late 1942 noted low effectiveness of level bombing against maneuvering naval targets. The phrase understated the crisis. Cause and effect formed a brutal chain. Ineffectual accuracy meant the Japanese reinforced forward bases by sea with acceptable losses. Allied ground forces faced increasing pressure on the Kokoda Track and around Bunagona. More enemy troops reached garrisons than fell to air interdiction. The air component was failing its mission. Something had to change. Kenney understood industrial warfare. He had served in World War I and spent the interwar years studying bombardment theory. He knew the pre-war models assumed stationary or slow-moving targets like rail yards, factories, and troop concentrations. Naval targets moved at 20 knots and could turn inside a bomb's trajectory. The doctrine didn't fit the problem. In October 1942, Kenney annotated a directive with a single instruction: evaluate low-altitude methods despite flak risk. Seek a controllable delivery window at sea. The margin note became an engineering order: test low-level bombing, quantify the risks, measure the accuracy. If the numbers improved, scale it. A B-25 Mitchell lined up on the test range east of Port Moresby. Altitude, 200 to 250 feet above the water. Indicated airspeed, 200 miles per hour. The pilot held heading and altitude steady. A bombardier triggered release manually. A 500-pound general-purpose bomb with a 4 to 5 second delay fuse dropped free. It struck the water nose first, ricocheted upward at a shallow angle, traveled forward, then detonated beside a hulk anchored offshore as a target. The bomb had skipped like a stone thrown across a pond. Conventional wisdom among aircrews warned that low-level attacks invited prohibitive losses. Enemy anti-aircraft fire intensified below 1,000 feet. Light automatic weapons, 25mm and 13mm guns, tracked easily at close range. Tracer streams converged. Aircraft absorbed hits. But structured trials supervised by Major William Benn showed stable approach geometry, repeatable fuse timing, and survivable egress profiles when executed correctly. Kenney and Whitehead observed tests from the beach. Range officers recorded approach angles, release altitudes, skip distances, and detonation points in logbooks. Data accumulated. Release envelopes tightened through iteration. Mast-height approaches placed aircraft inside a few hundred yards of the target at release. Number 28 type delay. Fuses allowed the bomb to skip once or twice, penetrate the water near the hull, then detonate below the waterline or alongside the engine room. Hydrodynamic pressure focused the blast against the ship's structure. Coordinated egress procedures called for immediate pull-up and bank away below 200 feet before anti-aircraft gunners could track effectively. Speed and surprise mattered. Hesitation invited disaster. A test memo dated November 1942 described results in clinical terms. Skip observed at 75 yards forward of target. Detonation abreast engine room. Hull rupture noted. Structural failure progressive. The physics worked. Low-altitude geometry reduced aiming error against moving hulls from ship lengths to feet. Missed distance collapsed. Hit probability climbed from 3% toward 30% in controlled conditions. The improvement was measurable and repeatable. But the method exposed aircraft to intense short-range defensive fire in the seconds before release. Trials proved skip bombing worked in theory. The human problem remained unsolved. Shipboard gunners had clear fields of fire against low-flying aircraft. A 5-second approach run at 200 miles per hour covered roughly 1,500 feet. During those 5 seconds, multiple gun mounts could fire hundreds of rounds. A single 25mm hit could cripple an engine. A burst through the cockpit killed the crew. Suppress those guns for 5 seconds, and skip bombing became viable. Leave them active, and losses would exceed any gain in accuracy. The bomber needed protection during the approach. It needed a strafer. Kenney's staff drafted a second engineering order in late November. Convert B-25s into gunships. Install forward-firing armament heavy enough to blind and suppress deck gunners during the approach. The concept: strafers precede skip bombers by seconds, hosing target ships with .50 caliber fire to force gunners under cover. Skip bombers release while defenses remain suppressed, then egress before guns return to action. Timing became the critical variable. The engineering challenge: build a Mitchell that could carry enough forward firepower without compromising flight characteristics. A B-25CD nose section rested on wooden trestles in the workshops at Eagle Farm, near Brisbane. The Norden bomb site and its mounting structure removed, leaving an empty compartment. Armorers measured hardpoint locations for Browning M2 50 caliber machine guns. Electricians routed wiring for synchronized triggers tied to the pilot's control column. Sheet metal crews fabricated blast shields from scrap aluminum. The transformation from precision bomber to aerial gunship required improvisation at every step. The B-25 Mitchell's designed role was medium bomber, according to Army Air Force's documentation. North American Aviation built it to carry bombs to targets and return. Depot workshops at Eagle Farm in Brisbane recast it as a gunship in practice, driven by operational necessity. Paul "Pappy" Gunn drove the conversion effort with relentless energy. Gunn, born in Arkansas in 1899, had served as a Navy pilot, then worked as a civilian airline captain in the Philippines before World War II. He evacuated his family after Pearl Harbor, stayed behind, and joined the Army Air Forces. He understood airframes, armament, and what worked in combat. North American liaison technicians advised on structural load limits and stressed skin areas. 3rd Attack Group maintainers fabricated mounts, ammunition feeds, and reinforcing doublers using hand tools and welding equipment. The initial configuration mounted 4 fixed .50 caliber Brownings in the nose compartment, aimed forward and harmonized to converge at 600 yards. Fuselage package guns followed, 2 .50 calibers per side, mounted externally on cheek blisters just aft of the cockpit. Total forward-firing armament, 8 Browning M2 .50 caliber machine guns. Each gun fired at approximately 850 rounds per minute. 8 guns synchronized, 6,800 rounds per minute combined. Ammunition feeds were sized for sustained bursts of 15 to 20 seconds. Sighting adjustments ensured convergence at 600 to 800 yards, the optimal range to suppress deck gunners without overflying the target prematurely. A depot conversion sheet dated December 5, 1942, recorded the layout in bureaucratic shorthand. 4 forward nose guns, 2x2 cheek packages, total 8 forward-firing .50 caliber. Install blast shields per sketch, harmonized to 600 yards. The first prototype completed conversion in mid-December. Gun harmonization tests followed at the Port Moresby range. Pilots fired at moored barges and measured impact patterns. The beaten zone, the area where bullets struck, measured approximately 50 feet in diameter at convergence range, sufficient to rake a destroyer's superstructure or suppress gun positions on a transport's deck. Taxi tests revealed immediate obstacles. The forward center of gravity shifted dangerously. 8 guns plus 8,000 rounds of .50 caliber ammunition added roughly 800 pounds forward of the aircraft's designed balance point. The nose-heavy condition affected rotation during takeoff and increased stall speed. Blast from cheek-mounted guns scorched fuselage skin within inches of the muzzles. Vibration from sustained fire loosened rivets near mount doublers and induced fatigue cracks in the airframe skin. Gun camera footage showed muzzle flash reflecting off the fuselage, creating visual interference for pilots. Maintenance logs documented rivet failures, skin buckling, and electrical shorts caused by vibration. Engineering solved the weight problem through systematic ballast and redistribution. Solving blast damage and vibration required further modification, but the concept was proven. A B-25 could carry enough firepower to suppress shipboard defenses. Whether it could sustain that firepower without structural failure remained an open question. The answers would come from operational testing and incremental fixes. A 3rd Attack Group crew chief chalked the main landing gear doors before engines start. He measured the squat, how much the struts compressed, after loading ammunition. 1,200 rounds per side, 450 rounds per nose gun. Total ammunition load, 3,600 rounds. Each .50 caliber round weighed approximately 2 ounces loaded in belts. The nose visibly dropped, the tail rose, the nose wheel strut compressed near its limit. Load charts tolerated incremental nose mass for bombs or fuel. 8 guns plus 3,600 rounds of ammunition pushed center of gravity forward beyond published limits. Depot engineers at Eagle Farm consulted North American load manuals and telegraphed Wright Field in Ohio for technical guidance. Squadron maintenance officers reported handling difficulties during takeoff rotation. Pilots needed excessive elevator authority to lift the nose. Stall speed increased. Approach speeds crept upward, reducing safety margins on short forward strips. Wright Field correspondents advised Kenney's staff on ballast options and equipment redistribution. The solution emerged through systematic trial. Install ballast in the tail, shift radios and batteries aft where possible, use selective fueling to balance the aircraft during combat missions, and adjust standard operating procedures for rotation and approach speeds. Pilots received supplemental notes for operating heavy nose configurations on long runways only. A field engineering circular issued in late December 1942 authorized modifications by serial number. Forward center of gravity, approaching limit on strafer-configured B-25 CD variants. Ballast of 150 pounds authorized at fuselage station 360. Relocate radio equipment aft per attached diagram. Limit fuel load to 750 gallons during combat missions to maintain aft CG margin. The added ballast, often lead bars or sandbags secured in the tail cone, restored acceptable handling margins. Aircraft rotated predictably at calculated speeds. Approach characteristics stabilized. Pilots adapted quickly to procedures for the heavier nose configuration. Maintainers tracked ballast weight and position in aircraft logbooks. Restored center of gravity margins allowed strafer conversions to scale beyond hand-built prototypes. 3rd Attack Group received the first production batch of 12 converted B-25s in early January 1943. Additional squadrons followed as depot capacity increased. Conversions proceeded at roughly 4 aircraft per week per depot facility, with balance problems solved through engineering iteration. Operational testing uncovered a second constraint. The airframe's original skin and structural mounts could not sustain prolonged forward fire without progressive damage. Blast effects and vibration-induced fatigue threatened to ground the strafer fleet before it entered combat. Solving durability became the next engineering priority. Post-firing inspection of the first operational strafers revealed scorched paint in oval patterns behind the cheek gun pods. Rivet heads showed fretting marks, microscopic movement under vibration, near mount doublers. Electrical conduits near gun barrels showed heat damage to insulation. One aircraft developed a skin crack propagating aft from a cheek gun hardpoint after a sustained firing test. Factory original skin thickness and internal frame spacing weren't designed for sustained muzzle blast positioned inches from the fuselage or for lateral recoil forces from side pod-mounted guns coupling directly into the airframe structure. The problems were predictable in retrospect. Solutions required incremental engineering under field conditions. Armorers documented deficiencies in Form 1 aircraft logbooks using standardized maintenance codes. Sheet metal crews fabricated reinforcements using materials available in theater, aluminum sheet stock, steel doublers, and rivets in standard sizes. Ordnance officers recorded failure modes and initiated modification proposals routed through 5th Air Force headquarters to depot facilities. The solutions emerged in stages through trial and observation. Install blast deflector panels angled to direct muzzle gases away from the fuselage skin. Add rubber isolators, salvaged from engine mounts or fabricated from local sources, between gun cradles and airframe hardpoints to dampen recoil vibration. Move cheek guns approximately 3 feet aft from their initial positions to reduce blast concentration. Upsize structural doublers at hardpoints from 16-gauge to 12-gauge aluminum. Re-drill mounting holes, oversize and install steel bushings. Route electrical cabling away from gun barrels and install heat-resistant sleeving improvised from asbestos cloth. A Squadron Form 1 entry dated January 15, 1943, recorded a typical fix in maintenance shorthand. Skin chafing observed at Fuselage Station 240, port side. Install blast deflector per modification number 12, sketch attached. Inspect condition after 300 rounds fired. Ground aircraft if crack propagation observed. Reinforcement modifications extended structural service life and made long strafing passes, 15 to 20 seconds of continuous fire, feasible without compromising airframe integrity or safety. Fixes propagated across the strafer fleet as aircraft rotated through depot-level maintenance. Gun barrels heated rapidly during sustained automatic fire. 50 caliber Brownings generated barrel temperatures exceeding 600 degrees Fahrenheit after a 20-second burst. Tropical moisture in New Guinea threatened belt-fed ammunition reliability through corrosion of links and propellant degradation. Maintenance crews developed field procedures documented in unit standing orders. Inspect gun barrels visually every 50 flight hours for erosion near the chamber. Rotate spare barrels through squadron inventory to extend operational availability. Store belted ammunition in sealed metal cans with desiccant packets until loading. Heat treat ammunition feeds, running them through makeshift ovens improvised from oil drums to drive off moisture before installation in aircraft bins. Monitor gun heater circuits to prevent electrical failures that allowed condensation inside mechanisms. The strafer platform became operationally reliable through iterative engineering fixes implemented at unit level and formalized in depot modifications. Pilots trusted the guns to fire when needed. Maintainers kept them operational in tropical conditions. The aircraft could sustain the pounding of repeated combat sorties. Now tactical doctrine had to choreograph suppression and delivery into a repeatable, trainable system. Strafers opened the window. Skip bombers delivered ordnance. Top cover protected the package. Timing mattered more than individual aircraft performance. Coordination converted individual capabilities into combined arms effectiveness. A briefing board in the 3rd Attack Group operations tent outlined strike composition with colored chalk. Lead strafer elements drawn in red, skip bomber elements in blue, top cover in yellow. Mixed formations risked confusion over target assignment, mutual interference during attack runs, and mid-air collision during egress under fire. Disciplined timing and role clarity converted that complexity into tactical advantage. Group commanders refined choreography through training sorties against offshore wrecks and moored hulks. RAAF Beaufighter squadron leaders coordinated cannon passes timed to suppress shore-based anti-aircraft positions. A-20 Havoc flight chiefs integrated their lighter attack bombers into the sequence, focusing on screening destroyers, while B-25s engaged transports. Typical strafer fit by early February 1943, 6 to 8 fixed 50 caliber Brownings firing forward depending on specific aircraft conversion standard. Some aircraft, after further field modifications pushed the concept to its limit, reached 10 to 12 guns by adding additional cheek packs and underwing pods. Each strafer also carried 4 500-pound general-purpose bombs with short delay fuses as secondary armament for use after strafing passes. RAAF Beaufighters contributed 20mm cannon fire, effective against bridge structures and shore installations, but less useful for sustained suppression of deck guns. B-17 Flying Fortresses provided high-altitude distraction, drawing flak, and forcing convoy defensive maneuvers that disrupted formation cohesion. A Strike Standard Operating Procedure document dated February 8, 1943, codified the sequence in numbered paragraphs. Strafer element precedes skip bomber element by 15 seconds, measured from initial firing pass. Strafer approach at mast height 200 to 250 feet, airspeed 200 to 220 miles per hour, indicated. Commence firing at 1,000 yards, cease firing at 400 yards, initiate egress turn below 200 feet altitude. Skip bomber element follows strafer egress line, offset 500 feet laterally. Release aimed at forward third of target vessel. Egress below 200 feet, diverging axis from strafer element to deconflict flight paths. Roll clarity reduced mutual interference and increased bomb placement accuracy. Each aircrew knew their task, timing, and egress route. Training sorties flown from Dobodura and Port Moresby validated the tactical sequence against non-maneuvering targets. Strafers executed the first pass, hosing target wrecks with 50 caliber fire that shattered superstructure, penetrated thin deck plating, and, most critically, forced hypothetical gunners to take cover. Skip bombers followed precisely 15 seconds later, releasing at calculated altitudes while suppressive fire theoretically kept defensive guns silent. Top cover fighters, P-38s and P-40 Warhawks, engaged any airborne interceptors and provided warning of approaching enemy aircraft. The package functioned as an integrated system rather than a collection of individual attacks. Logistics infrastructure had to sustain combat tempo at operational scale. Ammunition consumption models calculated requirements. Fuse allocations matched bomb types to target categories. Spare gun barrels tracked by serial number and flight hours. Gun heater maintenance prevented moisture-related stoppages. Humidity control procedures protected belted ammunition during storage and transport. The logistics tail stretched from Brisbane through Townsville to forward strips at Dobodura and Port Moresby. Without that tail, the tactical innovations meant nothing. Tempo depended on supply throughput. Wooden pallets stacked with ammunition cans sat on pierced steel planking near fuel bowsers at Dobodura Forward Airstrip. Belted 50 caliber ammunition, 150 cans per pallet, 400 rounds per can. Delayed fuse bomb stocks, 12 500-pounders per pallet, nose fuses already installed in protective caps. The physical reality of sustaining combat operations appeared in those pallet stacks. Theater distances, Brisbane to Port Moresby, exceeded 1,200 miles, and shipping bottlenecks through Townsville threatened sortie tempo more than enemy action. Gun reliability suffered in tropical moisture and heat. Southwest Pacific Area Ordnance officers modeled ammunition consumption using sortie data and burst length averages. Depot chiefs allocated available stocks across competing demands. Transportation liaisons prioritized ammunition over non-critical cargo on coastal freighters and C-47 transport aircraft. Ammunition consumption models calculated belts per aircraft per strike using operational parameters. One strafer-configured B-25 firing all 8 guns for 20 seconds, a standard suppression pass, expended approximately 267 rounds per gun. 8 guns, 2,136 rounds per aircraft per pass. Multiply by 12 strafers in a typical element, 25,632 rounds consumed per mission. Add training ammunition, test firing, gun harmonization, and maintenance checks, 30,000 rounds per day. Belts arrived from the United States in wooden crates via maritime shipping, 6 to 8 week transit times from California to Brisbane. Armorers at forward strips loaded ammunition into aircraft wing and fuselage bins during overnight turnaround, working under blackout conditions. Empty brass and links returned to depot facilities for inspection, cleaning, and reloading when time permitted, though most expended materiel was simply discarded due to logistics constraints. Fuse allocation matched bomb types to mission profiles and target categories. Skip bombing required delayed fuses, typically number 28 nose fuses with 4 to 5 second delays, allowing bombs to ricochet off water, penetrate near the hull, then detonate below the waterline or against the ship's side plating. Instantaneous fuses suited attacks against land targets, fuel dumps, and parked aircraft. Mixed loads caused confusion and required careful attention during ordnance loading. Stocks rotated first in, first out to prevent chemical deterioration in tropical heat and humidity. Fuses stored in sealed containers with desiccant. Ordnance personnel inspected fuse threads and electrical contacts before installation. Spare barrel management became critical as strafer operations intensified. 50 caliber Browning barrels wore through erosion caused by hot propellant gases. Barrel life, approximately 10,000 rounds under normal conditions, potentially less in sustained fire profiles. Squadron armament officers tracked barrels by serial number, logging rounds fired per barrel per aircraft. Inspection intervals, visual check at 5,000 rounds for throat erosion, replacement at 9,000 rounds or when accuracy degraded beyond acceptable limits. Spare barrels shipped from the United States as high-priority ordnance items. Armorers swapped barrels between missions using headspace gauges to ensure proper timing and safety. An ordnance signal from 5th Air Force Headquarters to subordinate units specified the system in numbered paragraphs. Allocate 1,800 belts 50 caliber per strafer aircraft per projected strike. Replenish unit stocks within 72 hours of expenditure. Report gun stoppages by code using attached format. Priority resupply, delayed fuses, 50 caliber ammunition, spare gun barrels in that order. Divert cargo space from non-essential items as required. Sustainment infrastructure turned a novel tactical concept into a repeatable operational capability. The logistics tail moved faster than enemy adaptation cycles. Reconnaissance elements detected the test case in late February, an 8-transport convoy forming at Rabaul, destination Leh. The entire system, strafers, skip bombers, logistics, training, doctrine, would face operational validation against a defended maneuvering target. 8 transports, 8 destroyer escorts, approximately 7,000 troops embarked. The opportunity was time-sensitive. Weather over the Bismarck Sea was unpredictable. The convoy would reach Leh in 3 days if unmolested. Kenney and Whitehead coordinated strike windows from headquarters. The mission launched on March 1, 1943. Reconnaissance mosaics photographed from 20,000 feet marked a column of ships in vertical echelon. 8 cargo transports, estimates ranged from 6,000 to 8,000 tons displacement each. 8 destroyer escorts, Fubuki-class and older types mounting 12.7 centimeter main guns and multiple anti-aircraft mounts. Speed estimated at 8 knots. Course plotted toward Huon Gulf and Leh anchorage. Japanese convoy staff anticipated Allied air attack. Previous convoys had endured bombing with acceptable losses, but operational planning assumed manageable attrition under coordinated anti-aircraft fire, fighter escort, and evasive maneuvers. They had survived raids before. This convoy carried 6,900 troops of the 51st Division for reinforcement of the Leh garrison, critically understaffed after months of combat and disease. Allied reconnaissance crews shadowed the convoy from altitudes above effective anti-aircraft range. Convoy commander, Rear Admiral Masatomi Kimura, experienced in escort operations. Kenney reviewed reconnaissance reports at 5th Air Force Headquarters in Port Moresby. Whitehead coordinated strike timing, aircraft availability, and weather windows. Meteorological conditions over the Bismarck Sea complicated mission planning. Cloud layers obscured the convoy intermittently, forcing reconnaissance aircraft to drop below 10,000 feet periodically to maintain visual contact. Shadowing procedures maintained continuous tracking despite weather. B-25s rotated on station, reporting position updates via high-frequency radio. A reconnaissance log entry dated March 1st recorded positional data in standard format. Convoy bearing 110 degrees true from Cape Gloucester, speed 8 knots. Formation, transports in column, destroyers screening flanks and van. Escorts counted 8. Weather, scattered clouds 5,000 feet, visibility 10 miles. Sea. State, moderate, wind east-northeast 10 knots. Positive tracking enabled layered strike planning. Altitude stacks separated B-17 medium-altitude bombers from A-20 and B-25 low-level attackers. Briefed ingress headings split anti-aircraft fire arcs and forced defenders to divide attention across multiple approach vectors. Each strike element received specific timing, altitude, and heading parameters. March 2nd, initial contact by B-17s attacking from altitude. Bombardiers released on calculated courses. Bombs fell in sticks. Water erupted in massive geysers around the convoy. Formation held. Destroyers maneuvered to screen transports, laying smoke and firing anti-aircraft barrages that filled the sky with black bursts. No ships sunk. Reconnaissance assessment recorded scattered near misses and possible splinter damage, but no mission kills. The convoy continued toward Leh, speed reduced slightly to 6 knots due to evasive maneuvering. March 3rd, strafer and skip bomber elements launched from Dobodura and Port Moresby beginning at 0600 hours. Mission planning allocated fuel reserves carefully. Combat radius from Dobodura to intercept point 280 miles. Loiter time over target limited to 15 minutes before mandatory return for fuel reserves. Timing depended on accurate reconnaissance updates transmitted continuously. The convoy entered Huon Gulf at mid-morning. Weather cleared. The system, 18 months of engineering, training, logistics, and doctrine, would prove itself operational or fail under fire. Crews manned aircraft. Engines started. Formations taxied. The strike launched into clear morning air. Gun camera footage recovered post-mission showed tracers converging across destroyer superstructures in continuous streams. Bridge windows shattered frame by frame in the film. 50 caliber rounds penetrated thin deck plating, ricocheted off steel structures, and suppressed gun positions through sheer volume. B-25s crossed target bows at mast height, approximately 200 feet altitude, closing at 220 miles per hour indicated. 8 guns per aircraft fired continuously, 12 aircraft per strafer element, 96 guns firing simultaneously. The combined volume, 6,400 rounds per minute, overwhelmed defensive fire through sustained suppression. Japanese convoy anti-aircraft doctrine expected attacks to develop as individual passes from varying altitudes and directions, allowing gun crews to track and engage targets sequentially. Continuous 50 caliber streams arriving from a single axis silenced multiple positions during the critical 5-second approach window. Strafer elements led strike packages by design. B-25s descended from 3,000 feet to wave-top altitude 3 miles from target. Pilots aligned on lead transport's bow, trigger at 1,000 yards. Tracers walked across water, then climbed onto the hull. Deck guns fell silent, crews either killed, wounded, or forced below cover by the steel hail. Suppressi on achieved for approximately 10 seconds, the strafer's firing pass, plus a few seconds of residual effect while defenders recovered. Third attack group, B-25 element, leads press through flak that intensified as destroyers reacted. RAAF Beaufighter sections conducted cannon passes from offset angles, raking superstructures with 20mm explosive rounds that detonated on impact, destroying radar sets, fire control equipment, and exposed personnel. Destroyer screens returned fire with main battery guns depressed to minimum elevation, firing proximity-fused rounds that detonated in air bursts. Tracers crossed from both directions, red from Allied guns, white-yellow from Japanese positions. One strafer took hits in the port engine and wing root but maintained formation. Another reported hydraulic failure but continued the mission. Strafers completed firing passes and initiated egress, pull up to 300 feet, hard left turn, descend back to wave-top altitude, exit below flak coverage. The window opened. Skip bomber elements followed exactly 15 seconds behind strafer egress, time to exploit the suppression window before deck guns resumed effective fire. B-25 skip bombers approached at identical altitudes, 200 feet, and airspeeds as strafers, 200 miles per hour. Bombardiers released 500-pound bombs with 4.5-second delay fuses at calculated range, approximately 400 yards from target. Bombs struck water at shallow angles, ricocheted upward in flat arcs, traveled forward, struck hulls at or below the waterline, penetrated through thin plating or into the water directly alongside, then detonated. Hydrodynamic shock-focused blast energy against hull structure, rupturing plates, flooding compartments, and causing progressive structural failures. An after-action report filed by 3rd Attack Group intelligence officer recorded observed results in clinical language. Intense strafing preceded low-level bomb release by strafer elements. Observed multiple deck gun positions silent at moment of skip bomber release. Bomb hits assessed, 4 transports, 2 destroyers. Secondary explosions observed on Transport Hotel and Transport India, suggesting fuel or ammunition detonations. Transport Juliet observed settling by the bow, pronounced list to starboard, speed reduced to 0 within 5 minutes of hit. The suppression window functioned as designed. Skip bombing geometry applied successfully under fire. Early ship losses confirmed through photographic reconnaissance. Destroyers moved to screen damaged transports, laying smoke and attempting to tow crippled vessels. The convoy formation disintegrated. Subsequent strike waves repeated the pattern through the afternoon of March 3rd and into March 4th. Strafers suppressed. Skip bombers delivered. Top cover. Engaged airborne interceptors, Japanese Army Ki-43 fighters launched from Rabaul, arrived over the convoy but were intercepted by P-38 Lightnings at altitude. The convoy could not reform effective defensive posture. Transports lost propulsion or steering. Destroyers circled to recover survivors, blown off sinking ships, or swimming from capsized hulls. By nightfall, March 3rd, reconnaissance confirmed 6 transports and 2 destroyers sunk. By dusk, March 4th, the final count, all 8 transports and 4 destroyers destroyed. Intelligence estimates, approximately 3,000 Japanese troops lost at sea, 3,900 reached shore in scattered groups without equipment or cohesion. The tally sheets would quantify the method's effectiveness against level bombing. Intelligence officers spread strike forms across folding tables in operations tents. Each form recorded sortie data, aircraft type, bomb load, release altitude, observed results, release counts, observed skips, bombs that ricocheted visibly, near detonations, bombs that exploded close aboard without confirmed hits, hull detonations, bombs that struck ships directly or detonated alongside with visible damage. Post-strike reconnaissance flights photographed wreckage fields, oil slicks, floating debris, and survivors in lifeboats. Japanese records captured later and post-war interviews confirmed ship identities and casualties, 8 transports, 4 destroyers, approximately 3,000 troops lost. Many aircrew debriefs initially assumed B-17 flying fortresses attacking from medium altitude, 10,000 to 12,000 feet, had inflicted the bulk of damage. Combat claims often reflected perception rather than measured fact. Photographic analysis and collated strike data revealed mast height and skip runs produced the decisive hits. Group S2 intelligence sections separated tallies by delivery method and altitude band. 5th Air Force intelligence staff cross-checked claims against reconnaissance photography. Photo interpretation specialists identified specific ships in sequential photographs, tracking damage progression through the battle. The compiled summary appeared in 5th Air Force Operational Analysis, dated March 10, 1943. The key data presented in tabular format, comparing delivery methods. Low-level bombs, 137, released by strafer and skip bomber elements. Assessed hits, 48. Hit percentage, approximately 35%. Medium-altitude bombs, 387, released by B-17 elements from 10,000 to 12,000 feet. Assessed hits, 29. Hit percentage, approximately 7.5%. Additional analysis broke down contributing factors: suppression effectiveness, release geometry, fuse reliability, sea state effects. The quantified advantage validated 18 months of doctrine development and justified expanding strafer conversions across theater units. Skip bombing achieved hit rates nearly 5 times higher than level bombing against maneuvering warships. The 3% problem, the crisis that initiated the entire program in August 1942, disappeared. 35% hit rates made anti-shipping strikes operationally decisive rather than marginally effective. Cost analysis, increased exposure to anti-aircraft fire, resulted in 3 B-25s lost to flak, 2 forced to ditch short of base with battle damage, 4 aircrew killed, 9 wounded. Benefit: convoy destruction, mission accomplished, lay garrison denied reinforcement. The exchange rate favored the attacking force decisively. Kenney cabled results to General Douglas MacArthur at Southwest Pacific Area Headquarters and to Army Air Forces Headquarters in Washington. Headquarters staff in Tokyo received initial reports from Rabaul and revised reinforcement planning for New Guinea. Large convoys to Leh ceased immediately. The risk was assessed as prohibitive. Barge traffic increased, dispersing cargo across many small vessels. Night movement replaced daylight convoy runs. Destroyers no longer escorted large formations of transports. The strafer-skip combination reshaped sea lift operational equations across the Southwest Pacific Theater. Enemy logistics adapted under pressure. Assembly lines in the United States took notice. North American aviation received technical reports and recommendations from Southwest Pacific Area via Army Air Force's Materiel Command. Field modifications tested operationally under combat conditions provided validated data for production engineering. The improvised strafer, built in depot workshops from hand-fabricated parts, would become a factory-standard configuration. Paul Gunn received orders routing him to the United States to consult with North American engineers on production variants incorporating forward-firing armament, structural reinforcements, and blast protection features derived from 18 months of field experience. The Mitchell Strafer entered series production. North American Aviation Assembly jigs at the Kansas City, Missouri plant held B-25 fuselage sections fitted with strafer nose configurations. Factory drawings specified gun positions, mount reinforcements, ammunition feed routes, and blast deflector installations. Paperwork routing Paul "Pappy" Gunn from Brisbane to Kansas City authorized him to advise on forward fire layouts, structural durability fixes, and operational lessons learned from combat employment. Theater improvisations rarely achieved series production. Most field modifications remained local expedients. The strafer proved different. Forward-firing concepts validated at Bismarck Sea matured into G, H, and J production variants manufactured by the thousands. Paul Gunn arrived at North American aviation facilities in May 1943 carrying technical reports, gun camera footage, maintenance, logs, and after-action summaries. North American engineers studied skip bombing results and strafer effectiveness data. Army Air Force's Materiel Command officers at Wright Field reviewed Southwest Pacific Area operational analysis documents and authorized production changes. The B-25G integrated a 75mm M4 cannon, adapted from the M3 light tank main gun, in a fixed mounting offset slightly to port, plus multiple 50-caliber machine guns. The concept: heavier forward firepower for attacks against fortified positions and shipping. Production: 405 G models built between August 1943 and March 1944. The B-25H standardized lighter armament, 8 forward-firing 50-caliber Brownings in the nose compartment, deletion of the bombardier position, addition of a fixed 75mm cannon similar to the G model, and cheek blister mounts for additional 50 calibers. Total forward firepower, up to 14 50 caliber guns, plus the cannon. The H model incorporated structural reinforcements and blast deflectors developed from Southwest Pacific Area field modifications. Mount doublers used heavier gauge aluminum. Gun feeds received improved environmental protection. Electrical systems routed away from high heat areas. Factory acceptance testing included sustained fire trials exceeding combat burst lengths. Production: 1,000 H models built between February and July 1944. The B-25J represented the final evolution. Strafer nose and bombardier nose offered as factory options depending on mission requirements. Units could select configurations during procurement. Strafer nose J models standardized 8 forward 50 calibers in the solid nose, cheek blisters with 2 additional 50 calibers per side, total 12 forward-firing guns. The J model also incorporated Pacific theater lessons on crew comfort, visibility, and defensive armament. Tail gun positions received improved fields of fire. Waist gun mounts standardized on flexible installations. Production: 4,318 J models built, the most numerous B-25 variant, manufactured from December 1943 through August 1945. A North American aviation factory circular dated June 1943 documented the engineering basis. Incorporate forward-firing armament per Southwest Pacific Area operational experience. Standardized cheek blisters per field modification patterns documented in 5th Air Force technical reports. Reinforce gun mounts to sustain 10,000 round endurance testing without structural failure. Install blast deflectors and heat shields per attached specifications. Ensure center of gravity remains within flight envelope across all loading configurations. Industrialization spread strafer capability across multiple theaters. North African units received strafer-configured B-25s for anti-shipping strikes in the Mediterranean. European theater units employed them against ground targets and tactical interdiction. Pacific units standardized on the configuration for all anti-shipping and ground attack roles. Reliability stabilized at scale through factory quality control and standardized parts. Field-modified strafers required constant maintenance to address vibration-induced failures and blast damage. Factory-built strafer variants incorporated engineered solutions that eliminated most durability problems. Ammunition feeds improved through redesign and better materials. Gun heaters became standard equipment rather than field expedients. Blast deflectors installed during manufacturing rather than retrofitted. Training manuals published by Army Air Force's Training Command codified mast-height doctrine, skip bombing geometry, and strafer coordination procedures. New aircrew graduates learned the tactics from initial qualification rather than discovering them operationally. Hardware standardization and doctrinal codification were complete by mid-1944. How did they reshape operations beyond Bismarck Sea? The Lake Convoy's destruction marked an operational turning point, but the strategic impact extended through subsequent campaigns. Sea lift strategy shifted across the Pacific. Japanese Naval Command adapted convoy procedures. Allied air forces applied lessons to other theaters. The strafers' influence reached beyond the Southwest Pacific area geographically and beyond 1943 chronologically. Bismarck Sea became a case study taught at staff colleges and tactical schools. The numbers, 35% hit rates versus 3%, validated innovation under pressure. A Japanese naval staff situation map showed the convoy route from Rabaul to Leh, marked with a bold red X. Marginalia in staff officers' handwriting noted alternatives: barge traffic, night movement schedules, cargo dispersal across multiple small vessels, submarine transport for critical supplies. Large escorted convoys, the standard method for moving division-sized reinforcements, were assumed sustainable before Bismarck Sea despite air attack risks. After March 4, 1943, that assumption collapsed. Staff assessments judged the risk prohibitive. No large convoy attempted the Rabaul-Lay run subsequently during 1943. Area Naval Command adjusted logistics procedures throughout the Southwest Pacific. Allied G2 intelligence sections summarized traffic pattern shifts in weekly reports. Unit operations logs noted changes in target availability and composition. The pivot appeared in quantitative data. Before Bismarck Sea, an average of 2.4 large convoys per month transited to Leh and Salamaua. After Bismarck Sea, 0 large convoys observed through June 1943. Barge traffic increased proportionally. Individual barges, wooden-hulled craft displacing 50 to 200 tons, moved cargo at night under cover of darkness and weather. Daylight transit ceased. Destroyers no longer escorted large transport formations. Instead, they conducted night runs carrying troops packed into destroyer spaces, landing them via small boats. The sealift equation changed fundamentally. Reinforcement tempo slowed from division-sized increments to company-sized dribbles. Leh garrison supply throughput dwindled from thousands of tons per month to hundreds. Medical supplies, ammunition, food, and replacement personnel arrived in quantities inadequate to sustain operations. Garrison strength declined through combat attrition, disease, and malnutrition without corresponding replacements. Allied ground forces, Australian and United States units advancing from Wau and the Markham Valley, faced weakening opposition. Allied interdiction adapted to target the new pattern. Patrol torpedo boats, PT boats based at forward anchorages, increased night operations targeting barge traffic with torpedoes, automatic weapons, and coordinated attacks. B-25 strafer units shifted focus to barge hunting missions, flying low-level patrols along coastal routes. 50 caliber fire shredded wooden barge hulls. 500-pound bombs sank steel barges with single hits. A-20 Havocs and bow fighters joined anti-barge campaigns with cannon and machine gun armament. No target was too small to justify a mission. Cumulative attrition exceeded replacement capacity. An Allied intelligence summary dated April 25, 1943, quantified the operational shift. Since March 4th, no large transport convoys observed on routes to Leh or Salamaua. Small craft traffic increased approximately 180% compared to pre-March levels. Night movement prevalent, daylight sightings rare. Estimated cargo throughput via sea reduced 70% from February baseline. Enemy garrison supply assessed inadequate to sustain current force levels. Denied mass reinforcement. Japanese forces in New Guinea fought defensive campaigns with declining capability. Australian 9th Division and United States forces captured Leh in September 1943 against weakened opposition. Logistics planning shifted accordingly. Allied commanders advanced timetables based on enemy supply constraints. What began as a field modification to solve a 3% hit rate problem altered theater sealift fundamentals. The strafer concept, validated operationally at Bismarck Sea, became doctrine that reshaped campaign planning. Skip bombing replaced level bombing as the primary anti-shipping method. Mast-height attacks became routine rather than experimental. The medium bomber's mission portfolio expanded beyond its original design parameters. North American Aviation's B-25 Mitchell, initially conceived as a level bomber for attacking ground targets, became the Pacific Theater's primary ship killer and barge hunter. Doctrine followed capability. Tactics followed technology. Outcomes followed innovation. A comparative analysis table prepared by 5th Air Force intelligence staff in October 1943 overlaid late 1942 approximately 3% claimed hit rates against mast height and skip bombing results from multiple engagements. Bismarck Sea 35%, Wewak Harbor Strikes June 1943, 31%. Hansa Bay Convoy, August 1943, 28%. The pattern held across diverse conditions: sea state, target maneuver, defensive fire, weather. Low-altitude skip bombing preceded by suppressive strafing consistently achieved hit rates 10 to 12 times higher than medium-altitude level bombing. B-25H and J production notes listed standardized armament configurations: 8 to 14 forward-firing 50 caliber machine guns, optional 75 mm cannon, cheek blister mounts, reinforced structures. The medium bomber classification, once synonymous exclusively with level bombing, now included a proven, documented, and factory-standardized anti-shipping role. Lieutenant-General George-C-Kenney's post-campaign reflections, recorded in operational reports and later in memoir, emphasized adaptability as the critical factor. "We had aircraft, bombs, and brave crews in August 1942. We also had 3% hit rates. What changed wasn't equipment, it was geometry, timing, and suppression. The same bomber, flown differently, with guns added and tactics refined, achieved 12 times better results. That's engineering warfare." Ordnance sections tracked ammunition consumption. 5th Air Force expended approximately 68 million rounds of 50 caliber ammunition between January 1943 and December 1944, much of it through strafer aircraft in anti-shipping and ground attack roles. Training circular authors codified mast-height doctrine in formal publications distributed to all Army Air Forces commands: approach parameters, release altitudes, fuse settings, egress procedures. Strafer nose configurations and cheek blister armament became factory standard options on B-25G, H, and J production variants. Low-level attack doctrine, formalized in training manuals, superseded pre-war level bombing emphasis for maritime targets. Delayed fuses remained critical components. Stockpiles maintained at theater level exceeded instantaneous fuse inventories. Integration with other aircraft platforms expanded the concept. A-20 Havocs, A-26 Invaders, and B-25 variants all employed forward-firing suppression combined with skip bombing. The principle proved transferable across airframes and theaters. European theater units adopted similar anti-shipping tactics against German coastal convoys in the Mediterranean and North Sea. Royal Air Force Coastal Command employed Beaufighters and Mosquitoes in coordinated strikes against Axis shipping, using variants of the strafer-skip combination. Post-war analysis by United States Strategic Bombing Survey examined anti-shipping effectiveness across theaters and concluded low-altitude skip bombing, when preceded by effective suppressive fire and executed with appropriate fusing, achieved hit rates exceeding 30% against maneuvering naval targets. This represented the most effective conventional air-to-ship attack method employed during World War II. The method's statistical superiority was documented and accepted. A 5th Air Force post-action evaluation dated December 1943 summarized the operational validation. Low-altitude attack, preceded by heavy strafing, is the surest anti-shipping method available in this theater. Hit probability exceeds medium-altitude level bombing by factors of 8 to 12, depending on conditions. Losses to anti-aircraft fire are acceptable given mission effectiveness. Recommend continued emphasis on strafer conversions and skip bombing training. The recommendation became policy. Doctrine spread globally. Training incorporated lessons. Future aircraft designs, particularly attack aircraft in post-war development, reflected the strafer's influence through integral forward-firing armament and low-altitude attack optimization. Production numbers documented industrial response. North American Aviation manufactured 9,816 B-25s total across all variants from 1940 to 1945. Thousands incorporated strafer modifications either as factory-built configurations or through depot conversions. G, H, and J variants, the strafer-capable models, represented approximately 6,000 units combined. Factory-built standardization eliminated field modification variability and maintenance burdens. The Mitchell became globally synonymous with low-level attack, ground support, and anti-shipping strikes. Paul Gunn's improvisation at Eagle Farm Workshops in November 1942 became an industry standard by 1944. Final operational marker from historical records: 8 transports and 4 destroyers sunk in a single convoy action. Large-scale reinforcement of lay by sea effectively halted. The 3% problem solved through engineering, validated through combat, standardized through production. 35% hit rates achieved. Field modifications transformed into factory specifications. Doctrine codified for global application. Problem: late 1942. Approximately 3% claimed hits against maneuvering ships. Medium bombers ineffective in anti-shipping role. Japanese sea lines of communication to New Guinea remain viable. Leh and Salamaua garrisons reinforced despite repeated air attacks. Solution: mast-height and skip-bombing delivery geometry paired with B-25 forward-firing suppression. Strafer aircraft precede skip bombers by 15 seconds. Continuous 50 caliber fire suppresses deck guns during approach window. 500-pound bombs with delayed fuses skip into hulls at waterline. Engineering, center of gravity restored via tail ballast and equipment relocation. Blast damage prevented by deflector panels and relocated gun positions. Vibration isolated through rubber mounts and reinforced doublers. Ammunition feeds protected against tropical moisture. Gun barrels tracked and rotated through inventory to maintain reliability. Effect: March 1943. 8 transports and 4 destroyers sunk at Bismarck Sea. Low-level skip bombing hit rates measured at approximately 35%. Medium altitude level bombing remained below 8%. Large convoys to Leh ceased immediately post-battle. Japanese sea lift strategy shifted to barge traffic and night movement. Estimated cargo throughput reduced 70% on New Guinea routes. Leh garrison supply inadequate to sustain operations. Allied ground advances accelerated against weakened opposition. Legacy: B-25H and J production variants embedded strafer armament as factory standard configuration. Low-altitude anti-shipping doctrine codified in Army Air Force's training publications. Skip bombing became standard tactic in Southwest Pacific, Mediterranean, and European theaters. Forward-firing armament influenced attack aircraft design through post-war period. North American manufactured approximately 6,000 strafer-capable Mitchell variants. Concept proved transferable to other platforms and theaters. Post-war United States Strategic Bombing Survey validated method as most effective conventional air-to-ship attack. The Battle of the Bismarck Sea demonstrated a fundamental principle: field adaptation, when supported by systematic engineering and adequate logistics infrastructure, can redefine operational capability inside a single campaign season. What began as a 3% hit rate, effectively mission failure, became a 35% hit rate through measured innovation, iterative testing, and doctrinal refinement. The strafer was not a miracle weapon or revolutionary technology. It was a methodical engineering response to a documented tactical problem, validated under combat conditions, and systematized through industrial production. Lieutenant-General George-C-Kenney and Pappy Gunn did not invent skip bombing. Multiple air forces experimented with similar techniques. They systematized it through engineering discipline. They solved the center of gravity problem with ballast and redistribution. They solved blast and vibration problems with deflectors and reinforcements. They integrated suppressive fire with precision delivery through choreographed timing. They built logistics infrastructure to sustain consumption rates. They proved effectiveness through measured combat results. They exported lessons to factories for production standardization. They codified tactics into doctrine for global dissemination. The innovation cycle: identify problem, engineer solution, test operationally, refine iteratively, standardize industrially, distribute globally, completed in 18 months. 8 transports rest on the floor of the Bismarck Sea at varying depths. 4 destroyers lie beside them in the silt. The wrecks remain unmarked, visited occasionally by technical divers, documenting Pacific war sites. They are silent monuments to adaptation under operational pressure. They mark the point where medium bombers transitioned from ineffective to decisive in the anti-shipping role, where field modifications became factory standard configurations, where 3% became 35%, where tactical innovation reshaped campaign logistics and strategic planning. The archival numbers, verified, cross-checked, and preserved in official records, document the transformation without embellishment. The story requires no dramatization. The facts suffice. Respectful, factual, conclusive. If you value fact-based military history rooted in primary sources and documented evidence, consider supporting this channel.